this one. Okay, so yeah, again, course overview. So the title is Lie Groups and Lie Algebras. And so what are they? Very rough definition, not precise at all. A Lie group is a smooth manifold that is also a group. We have to have additional conditions that the group operators are smooth functions, etc. But I'm going to do that later. So basically, it's a smooth manifold, a geometric object, which is also a group. So it has a group structure. So probably the simplest, non-trivial example will be a circle. Circle maybe in this plane. So this is a manifold, one-dimensional manifold, and we can also think of this as a group. Like, if you think of this as a complex plane, everything is like e to the I theta, so this forms a group. So it is a manifold, and also at the same time it's a group. So it's basically it's a manifold, it's a geometric object. Okay. And also another example, we will study this a lot in this semester. We usually denote it like this, and it's called a general linear group. As a set, it's a set of n by n invertible matrices over C, meaning the entries are complex numbers. So this is GLN is the main object in the first part of this chapter. So Lie group is something like that. It's a manifold. It's because it's a group, and we have multiplication structure here, and it is not difficult to see there is a manifold. So Lie groups are something like that. Now it's a very vague statement. And what about the Lie algebra? Because it's a manifold, one can think of a tangent space, and the tangent space of a Lie group is basically a vector space at the identity element as a group. And it happens that it is a vector space, and we can also give some multiplication structure there. So it is a vector space with multiplication. And usually denoted the multiplication using a bracket called a Lie bracket. And this gives us Lie algebra. So algebra is a vector space with multiplication structure, and Lie algebra is not just an algebra, but that have additional condition. So this bracket must satisfy some condition called a Jacobi identity. So Lie algebra is basically a vector space or algebra. So this came from tangent space of a Lie group, but we can give a definition without mentioning Lie group, just definition as an algebra. So algebra with Lie bracket, satisfying certain condition called. And an example of a Lie algebra is general linear algebra. So I'm writing using lowercase. So it's a general linear algebra. So it's basically, as I said, all matrices, all complex matrices, not necessarily invertible matrices over C. So we want to have a bracket, and the bracket operation is defined to be xy minus yx. So this multiplication is the usual multiplication in matrices, for the matrix. So if you have two matrices n by n, x and y, you can multiply x and y and then minus y and x, and this is defined to be the bracket. And this satisfies the Jacobi, what's called Jacobi identity, so it becomes Lie algebra. So this is the most fundamental Lie algebra. So we will study this and their subsets in this semester. So in this book, the title is, we have one more word, like representations. So what is a representation? So we now know, at least vaguely, what Lie groups and Lie algebras are. So now, what is a representation? So representation, we have to say representation of what? So a representation of a group, we can consider a representation of a group or representation of Lie algebra. So representation of a group, say G, is just a definition, thus the abstract definition is a homomorphism, a group homomorphism, because it's a group. Homomorphism, say from G to the general linear group. So it means whenever we have an element here in G, we assign to it a matrix, an invertible matrix. So it's homomorphism like that. So in some sense, a representation of a group means we somehow embed this inside a matrix group. So we want to think of this as a group of matrices. And in fact, this is equivalent to saying that G acts on a vector space V. So where V dimension of V is n. So representation of a group is basically group action on a vector space with certain, so we have to define what this really means, but not today. And so representation of a group is like that, and we can also consider representation of a Lie algebra, usually denoted like a Gothic character, is similar. It's a homomorphism, but now this is not a group, so it's not a group homomorphism, but Lie algebra homomorphism. So we have a structure, Lie algebra, so Lie algebra homomorphism, say psi, from this Lie algebra to the fundamental Lie algebra that we consider, so that's general linear algebra. So homomorphism means it preserves the structure of the algebra structure given by the Lie bracket. We have a Lie bracket here, we have a Lie bracket here, the bracket must be preserved. Again, this is the same as this G acts on, you can think of this as a G action on V. So this is a very vague explanation for these three terminologies, Lie algebras, or Lie groups, Lie algebras, representations. So if you're not familiar with this, probably doesn't make sense at all to you, but hopefully at the end of the semester, you will understand what this means. So basically, we will study these objects. More focused on the representations of Lie algebra, semi-simple Lie algebra. So this is a brief overview of what we are going to learn. And let's begin the first chapter then. So chapter 1, matrix Lie groups. So, as I mentioned, the first 5 chapters will be went through very quickly. So, unfortunately, I have to skip most of the proofs. I'm just tell you just the definitions and then properties that will be used later, and maybe skip most of the proofs. But if you want to know the proofs, then you can always read the textbook because everything is in the book. Basically, what I'm going to do is in the book. I'm not going to do something else. I just follow the book. Yeah. So, the first section, definitions. So, the notations that we learned today will be used throughout this semester. So, you want to get familiar with this. So, M sub n C, this is the space of n by n matrices with complex entries. So complex matrices, n by n, basically n by n complex matrices, complex entries. And of course, we can work with real numbers. Then if you can change Z by R, then it's just everything is the same, except that we use real numbers. And we've already seen this before. L, GL, and C, this is the general linear group. Over C, meaning group of invertible matrices in here. So n by n complex matrices. And similarly, we can consider GL and R. It's a general linear group. Everything is the same. Everything is the same, except we use real numbers. Yeah, I don't think we use fields other than R and C, so it should be that complicated. Shouldn't be that complicated. And because n by n matrix has n squared entries, we can think of these as vector space, the usual vector space, like M and C as C to the n squared, because there are just n squared entries. So when we have this, we can consider the usual topology. So we can use the usual. We can consider the usual topology. In here. So you can say that these two are close or they are far. Then we can talk about the distance, etc. And so let me define sequence. We have a sequence AM, or a sequence of matrices. So M is like that. So we have an infinite sequence of n by n matrices. And we say that the sequence AM converges to A as M approaches infinity. So in notation, we can write things like this. AM, the usual notation for the limit, if every entry converges to the entry there. So this, so okay. So basically, this means the JK entry is converges to the JK entry of A for all JK. Okay. So entry-wise converge. That's the definition of the convergence here. Okay. Now the definition that you need to remember: matrix Lie group. A matrix Lie group is a subgroup, say G of GL and C, right? So it's a group of matrices, invertible matrices, such that if AM is in G and if there is a limit, then either A is in G or A is not invertible. So it's a subgroup satisfying this property. So what does that mean? So in other words, so equivalently, we can say that matrix Lie group is G is a closed subgroup of GL and R and C. This means closed inside here, not in M, the whole space. Okay, it may not be closed in Mn, but it should be closed in GL. That's the definition here. Okay. So matrix Lie group is a closed subgroup of the general linear group. And we will see many examples of matrix Lie groups today. Let's look at an non-example. So, for example, G, L, and Q. So, of course, a set of or group of n by n matrices whose entries are rational numbers. This is not a matrix Lie group. Not a matrix Lie group. Why? It is a subgroup for sure, subgroup of this. It is contained in this group and it is closed under multiplication. But why? Let's consider a sequence inside this group. Like, let's consider n equals 2, and then let me construct a sequence like this: 1, 1, 1, 0, 1, 1, 1, 4, 4, 1. Now you guess what I'm doing, right? Like that. They are all inside this group. They are all complex rational numbers. But these approaches, we can choose these numbers so that these approaches to this matrix. Okay? So this, we have a sequence inside this group, and it has a limit to a matrix which is not in the group, but it is invertible. So it does not satisfy this. If it's not in the group, it must be somewhere else, not in the group. So this is not a matrix. Is this clear? Then let's ask you this question. Is this a matrix Lie group? GL and C? Of course, it is a subgroup of itself. That's for sure. If we have this condition, do we always have this? For, let's say G is this. And suppose that we have a sequence like that. It has a limit, and does the limit always lie inside this group? No. You can find something outside. But actually, this condition is satisfied like trivially, because if this is not there, what does that mean? It's outside of this group, but this is the set of invertible matrices. So it's outside, so it's not invertible. So this condition is trivially satisfied. So this is indeed a matrix Lie group. But by the way, my question was, can you construct a matrix, a sequence of matrices, invertible or invertible, whose limit is non-invertible? Yeah, there is a simple example, right? Something like that. So my question was, so first, fact, or of course G, L, and C is matrix Lie group by definition. And my question was something like that. Okay, let's construct 1, 0, 0, 1, very simple example, 0, 0.1, 1, 0, 0, 0.01, etc. This obviously approaches 0, right? It's not invertible. It's fine, because it's not invertible. It is not inside G, L, and C, but it is not invertible, so that's okay. So either the sequence, the limit is either inside the group or non-invertible. That's the condition. As the name suggests, it turns out that matrix Lie groups are Lie groups, although I haven't really gave you the precise definition of a Lie group. It turns out that it's always a Lie group. It's a proper subset, unfortunately. But it's interesting enough, so we will only consider matrix Lie groups, so that we don't have to worry too much about the geometry or smoothness, things like that. Matrices are quite concrete, so it's easier to deal with, easier to understand. But still, it has all the useful and important examples are matrix Lie groups. So in this semester, we will only consider matrix Lie groups. So the definition is easy enough. We have seen some non-example. So now let's look at examples of matrix Lie groups. So these examples will appear very frequently. So, I already mentioned this, but also GL and C, these are matrix Lie groups. It's easy to check. And definition, SL and C. It's called the special linear group. Over C. And as the definition is this. So this is called the special linear group. In the set of matrices, invertible matrices, so it's in GL and C, whose determinants are 1. So when we say special something, that it means determinant is 1. The special general linear group means just invertible. Special linear means determinant 1. And of course, we can talk about special linear group over R in the same way. I'm not going to write down. Yes. Okay, are these matrix Lie groups? Let's think about that. So we need to consider a sequence if AM, let's say, is in special linear group. R or C doesn't really matter. Suppose that we have a sequence in the special linear group and the limit exists and it is A. Then what can we say? So what do we need to check in order to see whether this is a matrix Lie group or not? We have to check whether A is in the special linear group or A is not invertible. But is A in special linear group? By the way, this means this is inside the special linear group means the determinant is 1, right? But what is the determinant of A? Determinant is a polynomial in the entries. So it's a continuous function. So if AM approaches A, then the determinant should approach to this. So it has to have the value 1. It has a value 1, that means it's in the special linear group. So that's good. So it's a matrix Lie group. We don't have to worry about the second part because the first part has been already satisfied. So it's just, yes, good examples. Special linear groups. What else? We have a couple more examples. A matrix, a complex n by n matrix is called unitary if A adjoint is the inverse. Here, A star, this means the adjoint of A. It means basically it's conjugate of the transpose. Basically, it means A transpose conjugate, which means the ij entry or jk entry is akj conjugate. Because the complex number, we have conjugate. So adjoint is conjugate of transpose. And a matrix is called a unitary if the adjoint is equal to the inverse. So it has to be invertible. Okay. So the definition, U of n, this is the group of n by n unitary matrices. Yeah, in fact, we don't know just yet if this is really a group. As I said, this is well defined, but is this really a group? Let's check. Yeah, proposition. Yes, it is a group. It's really a group. So it has the identity. Does identity a unitary matrix? Yes, identity conjugate is identity, transpose is identity. So because identity is inside this set. So, well, oh, it's a proof. Basically, it's a proof. yeah, I wanted to write this inside the proof. Just by definition, just check. And suppose we have two unitary matrices. So their multiplication must be unitary. So A, B, conjugate. We want to know that whether this is inverse of this, but this adjoint can be computed like that. And because both are unitary, you can replace B star by B inverse, A star by A inverse. And now we can combine them together like that. And yeah, that's it. The adjoint of AB is equal to its inverse. So AB is a unitary matrix. Okay. Now we have to check if A inverse is also unitary. So suppose A is a unitary matrix, then of course by definition A star is A inverse. We want to know what A inverse star is. So we want to know, is this equal to A inverse inverse? Is that true? Yeah, of course this is A. Is this equal to this? But the thing is, we can exchange the order of this. This is equal to A star inverse. Why? Why is this? But let's just assume that this is true. Then we obtain this immediately. Is that right? Because if we assume this, we want to know this. Because we know that A star is A inverse, this is going to be A inverse inverse, obviously. So go to that. So it remains to prove this thing, but that's not difficult. Let's do that right here. Proof of this. First of all, I is equal to A inverse, of course. And the star does the same. Now let's compute this. Now we can kind of put this inside like that. But what does this mean? This means this part multiplied A star is the identity. That means A inverse star is equal to the inverse of this, A star inverse. So that's it. So that's the proof. So A inverse is also unitary if A is unitary. So it is indeed a group. So you can say the group of n by n unitary matrices. Okay, then the question is, okay, it's a group, a subgroup of GLN because everything is invertible. Is this a matrix Lie group? To answer that question, let's look at an equivalent definition. Unitary means A star is A inverse, but of course this means A star A equals the identity. And this is equivalent to saying that, now let's just compute the entry here, just by multiplying these two. And this is equal to, what's that? L equals 1 to L, A, L, J conjugate, A, L, K equals delta J, K for all J, K, 1, 2, dot, 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 N. I just rewrote this as an equation because it's a conjugate, I exchange it J and L. So now, now that we know this equivalence definition, let's see what happens if we have a sequence, unitary sequence of unitary matrices, and AM approaches A, then what happens? We want to know whether A is in the unitary group or if it's not invertible. But is this, it'll be easier if this is, if you can conclude that this is indeed a unitary matrix. Then, the second is just, forget about that. Is this unitary? Yes, it is. Why? Just look at this. This means because AM is here, we have L equals 1. Let's just plug in AM there. AM, LJ component, AM, LK equals delta JK. We have this for all M. Okay? Because that's the definition of the unitary matrix. And because AM approaches A, this means every entry here approaches the corresponding entry there. So this, the whole thing here will approach to this. The whole equation will become this. But this means A is a unitary matrix. So the A is a unitary matrix, so it is a matrix Lie group. It is a matrix Lie group. Another definition. You will see many definitions today. SUN, special unitary group. So now you can guess the definition, what this means. Special means determinant 1. So it's basically unitary matrix consisting of, unitary matrices consisting of, whose determinant is 1. So it's matrix unitary such that determinant is 1. And so also matrix Lie group. You can check by the same method. If you have a sequence entirely lying inside this, approaching to another matrix, then that matrix, the limit must be a special linear, special unitary as well. All right. Let's consider another property of the unitary matrices. So we need to introduce the usual inner product. It's the usual inner product in Cn, say. That means xy for vectors, this summation j from 1 to n, xj bar yj. So we will take conjugate for the first vector. This is a standard inner product. And the fact is, from the usual basic linear algebra, for any A, n by n complex matrix A, x, a, y, and of course for any x, y in Cn, vectors, this is equal to A adjoint x, y. If you have a matrix here, you can move this to the other side, but you have to put this adjoint sign for any A and X and Y. So if A is unitary, then let's compute this. AX inner product AY. Here, because A is multiplied, we can move this the other side with adjoint by this fact. But if A is unitary, we know that A adjoint is the inverse. So this is the identity. So it's XY. So in other words, so this means usually we say in this situation, we say that A preserves the inner product. This means for all xy. For all xy, if we have this condition, then we say that the matrix A, or linear transformation A, preserves the inner product. So if A is unitary, it preserves the standard inner product, and it's in fact if and only if condition. If a matrix satisfies this for every x and y, it is indeed unitary. So proposition, proposition A is unitary if and only if it preserves the inner product for all xy. It's important that we have to have this condition for all xy, not just some. Let's see a proof. This part we have already done. It's done. The next here. AX, AY, we know that we can move this to the other side, and A star, AX, Y. And by assumption, this is equal to x comma y for all x and y. And or we can rewrite this by moving this other side. A star AX minus x comma y is 0 for all x and y. I just moved this to the other side and then computed it. But the simple fact is that in this situation, this must be 0. This form, bilinear form, we say that this is usually is called non-degenerate, meaning if u comma v equals 0 for all u, then v must be 0, or the same for the other one. But anyway, it's y, no matter what y is here, it is always 0. That means the first vector must be 0. Or, of course, A star AX equals x for all x. But that means this is the identity matrix. So yeah, that's the proof. So unitary means transformation, linear transformation preserving the standard inner product. Okay. And another property of the unitary matrix is that if A is unitary, then the determinant of A, the absolute value of the determinant is 1. Now proof is quite simple. A star A equals identity. We can take the determinant both sides. But determinant is multiplicative, so that we can split like that. But determinant of identity is 1. But of course, this is determinant A squared. But we took already the absolute value must be positive, so we get this. That's it. So unitary matrix always has determinant, absolute value of the determinant is 1. Okay, now let's consider real version of unitary matrix. So an n by n matrix, real matrix. Matrix A is called orthogonal if A transpose is the inverse. And O of n is the group of the orthogonal group. And it is the group of n by n orthogonal matrices. So orthogonal matrices are real matrices. But if a unitary matrix is every entry in a unitary matrix is real, then it is in fact orthogonal, because adjoint is really the same as transpose. Okay, and by the same argument in the previous proposition, if A is orthogonal, then the determinant is plus minus 1, because now it's a real, determinant is real. Determinant, absolute value of the determinant is 1, but now it's a real number, so it's plus or minus 1. Okay, now what's next? By the way, it's a matrix Lie group. Now, SON, this special orthogonal group. And of course, this is the set of matrices, orthogonal matrices, whose determinant is 1. And geometrically, SO special orthogonal group is the group of rotations. The group of rotations in Rn. So we can, in R3, we can imagine rotating about some fixed axis, about some angle, and they form a group. And ON is the group of rotations and also reflections. So there are more operations here. reflections. So they have geometric meanings, and they are matrix Lie groups, of course. Yeah, we have some more. Okay, another bilinear form. Omega, let omega be the skew symmetric bilinear form on R2n. Like this, omega of x comma y is equal to sum over j from z1 to n. Yeah, it looks a little strange at first sight. Minus x n plus j y j. Skew symmetric means if you change x and y, then we get minus sign. So skew symmetric bilinear form. And definition SP and R. This is the real symplectic group. So what's the definition? It's a set of matrices, 2n by 2n matrices, the 2n are, and it preserves, consisting of those preserving this bilinear form. So omega ax comma ay equals omega x comma y for all xy in R2n. Yeah, I'm not really an expert in this area, but I heard that symplectic group is really important in geometry. But I'm not a geometer, so for me, it's just a group or set of matrices satisfying this condition. Very abstract. But it does have very important geometric meaning, yeah, that I don't know. Anyway. We can rewrite this condition using a matrix. Let capital omega be this matrix, 2n by 2n matrix. Then this, okay. Then this bilinear form can be written in this way, x comma y. It can be written in this way. And using this matrix, the proposition is that symplectic group, the real symplectic group, so this condition is the same as this. Minus omega A transpose omega equals A inverse. So it means this condition is the same as this. They are the same. And proof is homework, is one of the homework problems, so it's not going to be difficult. And there's an interesting, so I'm not going to do the homework, the proof now. An interesting consequence of this is that if A is a real symplectic group, real symplectic matrix. Oh, I'm not sure if we say that, but A is in the symplectic group. Yeah, let's say that. Then we have this condition. Let's take the determinant, both sides. Then minus determinant of this, and determinant of transpose is the same as the determinant of itself. Determinant of omega equals determinant of A inverse is the determinant of A, the whole thing inverse, the same. But what is the determinant of omega? It's not difficult. Plus or minus 1. Doesn't matter because we have two of them, so you can cancel this. Okay. So, is that right? Oh yeah. Determinant of A squared equals minus 1. This is not what I wanted. I want plus. What happened? Okay. Oh, I see. Yeah, of course. It's not minus 1. It's minus 1 to the 2n, because no, it's a 2n by 2n matrix. It's not minus 1, so it's plus. Actually, it's plus. Is that okay? So it's plus. That means and now A is a real matrix, so determinant of A is equal to plus or minus 1. So we can conclude like that. The interesting fact is that, in fact, we always have plus. We always have 1. But it's not non-trivial fact. I'm not going to do the proof, but the fact I want you to know that it's indeed 1 always. Okay. And now we can do the same thing with complex numbers. So I'm going to define the omega bilinear form 2n in the same way, exactly the same way. So z, this is omega, this is w, j from 1 to n, z, exact same way, no conjugate or whatsoever. Like that. And then definition SP and C. This is the complex symplectic group. And as a set, it's a set of matrices, 2n by 2n complex matrices, preserving this bilinear form. So it's exactly the same. Z, W, Z, W. For all ZW. Complex symplectic group. Again, the fact is determinant if A is inside a complex symplectic group, determinant is always 1. So it's a known fact. And finally, we define one more group, SP of n. So we don't put R or C, just SP of n. This means complex symplectic group intersect unitary. Notice that symplectic, when you are dealing with symplectic stuff, dimension is always even, so we just write n. But the dimension is even, so for unitary we have to write 2n. And this is called the compact symplectic group. Already we know this and this, but we can rewrite the definition in this way. So it's a set of matrices, complex 2n by 2n complex matrices that preserve, this means it preserves this omega bilinear form. Right, for all complex vectors x, y. And also this means it preserves the standard inner product. So it preserves, the matrix A preserves not only this, but also this. So together, it preserves both x and y for all x, y, 2n. So it's a compact symplectic group. Okay. So these are they are all matrix Lie groups, and we will study them in more details. Let's do a little more on the next section. Topological properties. We already mentioned the compact, but the definition is as follows. A matrix Lie group, G, inside GL and C. This is called compact if it is compact in the usual topology in M and C as topological space R to the n squared. This complex number can be considered as R2, so it's R2 times n squared. Okay, Euclidean space. We can talk about the compact or topology, but this is a Euclidean space, so compact means is equivalent to closed and bounded. So compact means closed and bounded. That's the same in this case. So G is compact. That means closed and bounded. But be careful that closed here means closed in Mn, not GLN. Because it is already closed in GLN always by definition. It's closed in the whole space. An example, these matrix Lie groups, SON, UN, SUN, SPN. This is compact symplectic group, so yeah, it should be compact, right? Compact. How can we show that? Closed, we can check closed and bounded, these two things. Closed is simple because closed is simple, easy. For the boundedness, let's consider just this, the first thing. The remaining groups can be done similarly. If A is a orthogonal matrix, then A transpose A equals the identity. Okay? But this means each column has length 1. We can rewrite this in this way. J from 1 to n, a j k squared equals 1. From this, you can obtain this. But now, everything is less than or equal to 1 because they are squared equals 1. So because every entry is bounded by 1, it is bounded. So it's closed, bounded, so it's compact. So this can all be done similarly. On the other hand, SL and R, special linear group, this is not compact. It's not bounded because let's say AM is this matrix, 1M, 1 over M, and 1, dot, 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 1. So diagonal matrix like that. M just a positive integer. The determinant is 1, so it is inside this group, but it's not bounded. M can be arbitrarily large, so it's not bounded. So it's not compact. But these groups are. I see. I think I should stop here and then I will continue next time. Yeah. Thank you for your attention.